Hello guys, I hope you're doing well. Can you hear me?
Everyone who hates
Okay, I think I see myself, so everything must be okay. Let me also update this stream in CF. Okay, is everything fine? How are you guys doing? Okay. Nice. So guys, as you know, today we're gonna talk about trees. We're gonna solve so many problems, so many tree problems, and I chose some of the problems that are gonna be really helpful for you, some of the best problems about this topic, and they are from easy level to harder levels. So we start with easy difficulties. We start with problems that are easier relatively, and we go to the problems that are more challenging and harder in comparison. And I've chosen all the problems in a way that they do not need a lot of knowledge, so I try to make sure that they do not need any sort of advanced topics to know, but they need to reach some good ideas in order to be able to solve them. So I hope that that would be helpful for you guys. Are you ready to start with the first problem? One suggestion is to try to explain solutions thinking the audience is noob, please. Okay, can you please first explain some basics of trees? Yeah. Yeah, so we will get to them. We'll get to the problems, and yeah, I believe that you can learn a lot in this topic stream by solving these problems. Yes, so basically, first of all, do you guys know that what is a tree? First of all, let's say what is a tree. Can you guys define a tree? What a tree is? So we want to first make sure that everybody are okay with this. We're gonna spend a little bit of time on this, and then we're gonna talk about the problems. Exactly, it is a graph, and it has no cycle, and it is connected. Exactly, yeah. Exactly. All of these conditions are true. So a tree, as you guys know, I just write it here to make sure that everybody are okay with this. And then we'll move on to the problems. So a tree is a graph where it has three properties, three main characteristics. One of them is that it is connected. One of them is that it has no cycles. And one of them is that it has n-1 edges. If it has n vertices, it has n-1 edges. And it can be proven that if you have any two of these characteristics, you're going to have the other one as well. So even if you show that a graph has two of these characteristics, for example, it is connected and it has n-1 edges, then you can be sure that it also has no cycles. Or if you show that it has n-1 edges and no cycles, then you can also show that it is connected. So any two of them are enough. The third one will be, from any two of them you can conclude the third one. So a graph with these three properties is going to be called a tree, and a tree will look like this. Something of this form. It's a specific part of a graph, and it is going to be super important and helpful in many modelings. And we're going to see that how this type of problems, this specific type of graph can be used to solve problems. There are so many problems that are defined on trees, and in modeling they are also very important. In the real world we see many things that we can model them to trees. So yes, also we can say that in a tree any two nodes of a tree has a unique path between them. Yes, these are also correct. So I adjust my cam. I think I should come to right towards the bits. Thank you very much for mentioning that. So let's now talk about the first problem that we want to discuss today. The first problem is Kefa and Park. This one 5ADC. I put the link of the problem in the video description as well. It's the first problem. It's relatively the easiest one. And it is a very interesting problem to see that's how we can solve a problem on a tree. It says that Kefa decided to celebrate his first big salary by going to the restaurant. He lives by an unusual park. The park is a rooted tree consisting of n vertices with the root at vertex 1. Vertex 1 also contains Kefa's house. Unfortunately for our hero, the park also contains cats. Kefa has already found out what are the vertices with cats in them. The leaf vertices of the park contain restaurants. Kefa wants to choose a restaurant where he will go. He's afraid of cats. So far we have a tree. In some of the vertices there are cats. Kefa is afraid of cats. The restaurants are in the leaves. He can go to any of the restaurants if and only if in the past from his house in the root of the tree to this leaf there are no more than m consecutive vertices with cats. You have to count the number of restaurants where he can go. Okay, and guys, let me also tell you that in this session we are having 3 problem solving sessions, so that's why I didn't focus a lot on defining trees, etc. I just said a summary of it. I'm assuming that you guys know some things about the trees. For example, a rooted tree is just a tree that you have chosen one vertex as a root and everybody are from that root. So I'm assuming that some of the things are already known by you guys and you're coming here to see how we can solve so many problems. If you had any issues in any parts, let me know for sure. So let's talk about this problem. In this problem, we have a rooted tree. It says that Kefa's house is in the root. Of this tree. This is Kefa's house here, and there are restaurants in the leaves. The vertices without any children. These are the leaves. The vertices without any children. And he can go to any of the restaurants. Some of the vertices have cats. He can go to a restaurant if and only if in his path to that restaurant there won't be more than m consecutive cats. It won't be more than m consecutive cats. This shouldn't happen. You have to say that how many restaurants are good and we can achieve them. Okay. So basically the main idea in here is that we can do a DFS. We can start from the roots and do a DFS. When we are on a vertex, like vertex V, we can just keep track of how many cats we have seen so far. How many cats we have seen. And this counter, when we see another cat in the new vertex, will be added by 1. When we see a vertex without any cat, it will reset to 0. Because we care about consecutive cats. So whenever we see a vertex without any cat, it resets to 0. So when we run this DFS, when we go to a vertex like V, first of all, I say that in the inputs, you can see that you are given these zeros and ones. If there is a 0 in a vertex, it means that there is no cats. If there is 1, it means that there is a cat there. So I can say that if A of V was 1, CNT must be increased by 1, else CNT must turn into 0. And then I can say that if CNT was greater than M, I can return and do not go inside this DF, inside the subtree of this vertex. Because I've already seen, in my past, I've already seen more than M cats. And then it's not, I cannot go this far. So I can return instantly. This vertex is not a good vertex for me. And anything in its subtree is not good. And then I can say that at the end, I can say that I can go to all the children of this vertex. And if that vertex was a leaf, I can add 1 to the answer. So I can see that if that vertex, for example, had degree 1, if degree of, as soon as I've defined degree, and degree is the number of children of a vertex. If degree was 0, or let's call it children, if the number of children of this vertex, something that I've calculated before, for example, it was 0, ans plus plus, this is a leaf, this is another answer for me, then 4 int u g of v, I can run DFS of u and CNT. If u was not equal to parents, I can also pass the parents to this vertex. I mean, in DFS, when we run a DFS, usually, when we run a DFS on a tree, we usually pass parents as well to the DFS, so that when we go over all the other adjacent vertices, we do not go to parents again. We will go to all the adjacent vertices of u except parents, because we were in parents just before this step. So we say that if u was not equal to par, just run DFS of u, its parent is v, and the CNT will be passed to it as well. And this way we can calculate that how many of these leaves are good. So basically we are just running a DFS and we keep track of how many cats we have seen so far, how many consecutive cats we have seen so far. And if it was greater than M, we just instantly return. We know that there's no good leaf in here. Otherwise, when we reach a leaf, we will increase our answer by 1. And then anyway, for any vertex, we will go to the children of this vertex and pass the current CNT to it as well. So is it clear? Is the solution clear? I will show you my code here as well. I will show you the code my code for this solution as well. But if it is clear so far, please use this emoji or put a plus in the chats. I'm new to your channel. Nice. Yes, I cover range queries in future as well. Let's see what comments I've missed. Do you study mostly during the day or night? Mostly during the night. I'm better with the night. How many problems are we going to solve? 5 problems, I think. I have more problems as well, but based on experience, we can solve around 5 problems in the stream. Nice, nice. So let me also show you my code. Here is my code. It's from when I was an expert. I solved it in contest. It's from 2015. It's now been around 10 years. It's just crazy. So I get the tree, I seen all the AIs, all the adjacent vertices, I get them, and then in DFS1, I just did DFS1 to see that which vertices are leaf vertices. So if leaf of where is 1, I mean based on how I coded there, it doesn't really make sense. But anyway, I implemented it like this. If leaf of where is equal to 1, it means that that vertex is not a leaf. If it is 0, it means that it is a leaf. It doesn't make sense, but this is how I implemented it back then. So I say that if u was not visited, then I set leaf of where equal to 1 because it's not a leaf anymore, it has a child, and then DFS1 of u. And then in DFS2, I do what I said. I just keep track of the CNT, and then I will update the CNT when I go to a vertex. And if I say that not of leaf of where, it means that this vertex was a leaf. Add 1 to the ans, and then go to all the other vertices as well. And as you see in my DFS, in here I have a DFS on tree, I'm using a visited array. But as I said, you don't need visited array as well when you have DFS on trees. You can just keep track of what was the parent of the current vertex, and you can just make sure that you will not go to that parent vertex. You will go to all the adjacent vertices except that parent vertex, because that parent vertex is the only vertex that is visited when we come to a vertex. So you could just pass a parent, you could ignore having this array, and instead pass the parent and just do not go to that parent and go to all the other vertices. So is it completely clear? You can solve it with BFS as well, that would also work. 2 topic streams every week. I think if it would be 2, it would be harder for you guys to follow as well. So I mean, I'm trying to make sure that you guys can also follow the topic streams as well. Maybe more than one, it would be hard for you. But I'm so happy that if you're learning from them and enjoying them. Where are you doing out degree of nodes? Yeah, I just keep track of if that vertex is a leaf or not. If leaf of where is equal to 1, it means that it's not a leaf in this code. Because when I see that a vertex has a child, I say that it is not a leaf. And then in here, I say that if it was leaf, not of leaf of where, it means that if it was a leaf, add 1 to ans. If it makes sense, please use this emoji or put a pause so that we will move on to the next problem. Write your CF ID. Yeah, we can also, I mean, one other thing that you can do to check a node is a leaf. What I did in my code was not the best possible way. The code is from 10 years ago and I was a junior back then. But if I want to code it right now, again, there's a better way to code it. Because in here, you can, for example, have a Boolean and just see that if you have called any vertex or not. If you came in here and called any vertex, you can set that Boolean to true. And if that Boolean was false, after this for, you can just add 1 to ans. So, because if that Boolean was false, it means that you had no child, so this vertex was a leaf. So, this would be easier than having another DFS to find the leaf vertices. So, yeah, for example, you could have a Boolean. If you called any child, you set that Boolean to true. At the end, if the Boolean was false, just add 1 to your answer. That would be easier. No, I do not use a stack to run DFS. I just use recursive functions. That would be very problematic if you want to implement recursive functions yourself by stacks. It's not very easy, I think. To write the DFS as a lambda function in the main function or global function. I think it's simpler to have it as a global function. Especially at the beginning, it's easier to, it's easier if you just focus on solving problems at the beginning and just define it as a global function would be better. Because it would be just simpler. You can also use lambda functions. But it's better if you just focus on solving problems, etc., than how to do these techniques of coding. At the beginning, especially, the most important thing for you is to see so many problems and their solutions and trying to solve them. So the main thing that you have to focus on is that. Nice. Okay, are you ready for the next problem then? Shall we move on? Okay, nice. So let's move on to the second problem, distance in tree. This problem says that a tree is a connected graph that doesn't contain any cycles. The distance between two vertices of a tree is the length in edge of the shortest path between these vertices. You are given a tree with n vertices and a positive integer k. Find the number of distinct pairs of vertices that have a distance of exactly k between them. Note that pair uv and vu are different. You came just in the best time. I'm starting and talking about the second problem. So this problem says that you have a tree that does not have any cycles, and the distance is the number of edges in the path between two vertices, and you are given a tree with n vertices and the number k. You have to find out how many vertices have distance exactly k between them. You need to count the number of vertices such that their distance is exactly k. Okay. Thank you, Manas. Yeah, this is a Persian sentence. Yeah, so let's see that how you can find that out. Is the statement clear? So we have a tree. We want to find out the number of pairs such that the number of edges in their path is exactly equal to k. Like this. We want the distance to be exactly k. Well, the point is that let's assume that we only want to see there. Let's take a look at the constraints. We see that n is up to 50,000 and k is up to 500. So n is at most 50,000 and k is only up to 500. So I say that let's find out for each vertex like v. Let's define like num of v and I as the number of vertices inside the subtree of vertex v, vertices below v, such that their distance to v is equal to I. Okay, so num of v and I is the number of vertices below v. They are in the subtree of v. V is their ancestor. So we just choose a vertex as a root. We choose a vertex, for example, vertex 1, an arbitrary vertex. Like vertex 1 as our roots. And then we see that first of all, how many vertices below some vertex, like v, are at distance I from them. And that can be easily calculated, right? Whenever you saw that v has a child like u, for any child like you can say that num of v and I plus equal to num of u and I minus 1. Right? This way it would be easily updated. If the vertex is gonna have distance I to v, it's one of the options is that for this child u, the distance of them to u is I minus 1. It is the case where they are going to be in this subtree. Okay, initially only num of v and 0 is equal to 1, the rest of the nums are 0, and then from the bottom you will start updating all these values. And the point is that whenever you add another vertex, another child like u in here, assume that vertex v has had some children so far, they are added. So num of v and I for any I is something that only these children are calculated so far. So num of v and I is only based on these children so far. And v is going to be added right now. So we are only considering right now in num of v and I, only these vertices had effects. So for these vertices, you have done this. For any I, you had num of v and I plus equal to num of these, for example, u primes and I minus 1, and now you're adding this child u. Before doing this, before updating num of v and I, what I can do is to have a for on, like for example, some j from 0 to k. I can have a for j from 0 to k, and I can say that I can add to my ans num of v and j. It means that the vertices are below the vertices that are below v by distance j in here. It must be in here in this red part, because as I said, vertex u is not yet added to vertex v. I mean, I have not updated, I have not done this for vertex u yet. So vertex v is not updated by this subtree or the subtrees after that. So right now it only has the subtrees that are processed before u. So I can say that ans plus equal to num of v and j times num of u, and can you say what? Can you say num of u and what? It must be added. We want we want the pair of vertices such that their distance is equal to k. K minus j, you're very close to the answer. Almost k minus j. It's num of v and j times exactly num of u of exactly Sujal. Yes, as Sujal says, it's gonna be num of v and j times num of u of k minus j minus 1. So it means that this is vertex v, this is vertex u. It says that try to find out how many vertices have in here. As I said, only vertices in here are processed for v. I say that let's see that how many vertices are at distance j from v, and multiply it by the number of vertices that are at distance k minus j minus 1 from vertex u and are below you. And then you can easily see that the distance between two vertices is going to be j plus this 1 plus this k minus j minus 1, which is going to be k. So therefore, we are going to have the number of pairs that their distance is going to be equal to k exactly. Yes, sure. I will update. I will repeat these parts. I say that I'm trying to update these nums. What I'm doing here is I'm just saying that num of v and I is gonna be the number of vertices. Num of v and I. The definition of it. The definition of num of v and I is the number of vertices that are in the subtree of vertex v and their distance from v is equal to I. Their distance from v is I. Okay. They are the vertices in the subtree of v such that the distance from v is I. So I'm saying that when you add another child like u to v, when you see this child and you run the DFS on this child, you can say that if there is a vertex in the subtree of u at distance I minus 1, it is also in the subtree of vertex v at distance I. So I can say that I can add to num of v and I all the vertices that are from distance are in distance I minus 1 from u. So num of u and I minus 1 must be added to num of v and I. Okay. And before adding these values, before updating this u, I mean these children of vertex v are added to v one by one. They are added as children one by one. And by added, I mean that they will update num of v. Before, I mean, for example, when this one arrives, this one is already added and this one is already added. Now I want to add this one. Before adding this one, I will have a for on all the possible j's and I will add to my answer num of v and j times num of u and k minus j minus 1. First, I add this value to my answer, and then I will update that dp. That's nums. Yes, the base case, as I said, is going to be num of v and 0. The best case is that num of v and 0 is initially 0. All of it is going to be simpler when I show you my code. I will show you my code now, and I will explain it there as well, and everything will be easier. So initially num of v and 0 is equal to 1 for any vertex, because this is the vertex itself, vertex v itself. In the subtree of v itself is there, and its distance from v is 0. And then all the other distances will be calculated, and the answer will be calculated based on that as well. In my code, I think I used DFS, yeah. So let me see. Also, this problem has other solutions as well. Let me show you my code. Yeah, it seems that I use BFS on my code in here. So let me show you my code. I get all the vertices. I mean, this code is also from around 10 years ago. This is also from 2015. So if you see that the way that I implemented code is weird, for example, I've defined 4s, it's because of that. It's from back then. So I initially set dp of I and 0. dp is that num that I was mentioning. dp of I and 0 is initially equal to 1. Okay, dp of I and 0, the number of vertices in the subtree of vertex I at distance 0. It is initially equal to 1. And then this num, I run a DFS. In my DFS, I try to find out the number of children of each vertex. In this DFS, if you take a look at this DFS, the only thing that it does is to find out how many children a vertex has and what is the parent of each vertex. So the way I implemented it is like this. I try to find out how many children a vertex has and what is its parents. And first of all, I will add all the leaves to this queue. I implemented it in a very hard way. There are easier ways to implement it, as I mentioned, and I will explain as well. But what I did is that I first add all the leaves to this queue, and each time I take a vertex from the queue and I want to add it to its parents. So each time I want to add a vertex to its parents, update its parent based on its values. Right now, all the vertices are separated from each other. For all the vertices, only dp of I and 0 is equal to 1. I want to start from the leaves and add their values to their parents. I pick one of these leaves, and then I say that I have for I from 0 to k, I say that ans plus equal to dp of a and I times dp of parent of a and k minus 1 I minus 1. This is exactly what we saw in here. I want to find the number of vertices in the subtree of a at distance I, multiply it by the number of vertices at the subtree of parent of a at distance k minus I minus 1. This make a pair with distance k. And then I add this vertex to its parents. I say that for any I from 0 to k, dp of par of a. And I plus 1 plus equal to dp of a and I. And then num of par of a minus minus. Now that parent has one less child to be processed, to be added to. Whenever this value became 0, this vertex can be added to its parent as well, because all its children has been added to it. And so I said that if num became equal to 0 and that vertex was not the root, q dot push parent of a and then q dot pop, and at the end see out ans. And this way the answer can be calculated. Does it make sense? If it makes sense, please use this emoji or put a plus again. What is the base case? Yes, that's what I answered. The base case is only dp of v and 0. Yes. No, it's not in and out dp. What I did, I could easily be done by DFS as well. I can write it for you guys. Yes, so many theory problems use dp ideas. Yes. Did you want all children of each subtree? Yeah, I mean, let me explain it in here. So what we could do is this as well. I mean, we can write it like this as well. We can have a DFS and have int of v, int of par equal to -1. What we can do is this. I mean, we can say that initially I want to see that how many vertices in my subtree are at distance I from me. And I'm going to call that as, for example, like dp. As you see in many tree problems, dp will be used as well. So initially dp of v and 0 is going to be 1, because initially we only have one vertex at distance 0 from v, and that is v itself. So initially we can set dp of v and 0 equal to 1. Okay. And then I'm going to go on all the other vertices that are adjacent to vertex v, int u, g of v. First of all, I say that if u was equal to par, continue. This is my parent, this is not the child. I only want to talk about the children right now. So if u was equal to par, I should continue. Otherwise, I should run DFS of u and v. DFS of u and its parent is v. And first, I will update my answer, and then I will add this child as a child of vertex v. I'll do it like this. I have for I from 0 to k I plus plus. First of all, I say that and plus equal to dp of v and I times dp of u and k minus I minus 1. What does it mean? It means that, okay, you have this vertex v. Count that how many vertices are at distance I from it and multiply it. This is u, a child of v. And then multiply it by the number of vertices at distance k minus I minus 1 from u. All these pair of vertices are going to have distance equal to k. Exactly. Right? All these vertices have their distance equal to k exactly. And then after that, add to dp of v and I. After that, you use dp of v and I here. Now you can update it for the next calculations. dp of v and I must be added by dp of u and I minus 1. And this way everything will be updated and you will have your answer at the end. So basically you are calculating that how many vertices are at a specific distance from each vertex v, and then you can just add to dp of v and I, dp of u and I minus 1 after updating your answer. And this is how everything will be calculated. Is it clear? Yes, it is trees as well. I mean, basically, they're dp on trees. I mean, this problem was being mentioned because you need to see that how. I mean, this is one of the most important topics again in problems on trees. One of the most important topics is dp on trees. So among the problems that you have on trees, dp will be used as well a lot. I mean, this is a very important subset of problems on trees, that you use a dp on tree. This dp was to find out how many vertices are at a specific distance from this vertex. If root node is chosen randomly, okay, that's a very good question. No, the point is that in here, no, it does not make any change. I mean, basically what we are doing is that we put one vertex as our roots, and we try to count every pass. When we choose a root, every pass of length k will look like this. When we choose this vertex as a root, we will count this pass in this vertex, in the vertex that is topmost. In future, we will find out that this is called the LCA of these two vertices u and v. But anyway, when you see this vertex roots, this pass will be counted here. If you choose another vertex as your root, maybe this pass will be counted somewhere else, like in here or like somewhere else. But this pass again will be counted somewhere. So the only change that will be made is that where you will count this pass. But all the passes will be counted in all of these ways. So choosing the root will not change the answer. It will not change the answer. Can you once again explain your BFS solution? It was not BFS. I think it was a bad way of doing DFS. I mean, it was a complicated way of doing DFS. I could just easily do all of these things in a single DFS. But what I did is that I tried to just process all the vertices from the leaves. That's basically the same thing that I did in here, only I just, instead of doing this in the same function of DFS, I tried to store all the leaves, all the vertices that they don't have any children. Initially, each vertex has some children. I will count the number of children that each vertex has. And if for a vertex, if the vertex did not have any unprocessed child, right now, I mean, num is equal to the number of children, but later on it will be the number of unprocessed child. If a vertex did not have any unprocessed child, it is ready to be pushed to its parents, to update its parents. So I say that if num of I was 0, q dot push I, and for that vertex, it means that if num of I is 0, it means that this vertex is ready to update its parents. And in my queue, it will be pushed into the queue, and then as long as q dot size was not 0, I consider the first element of q, and I say that first I go on its parent, and I say that ans plus equal to dp of this vertex, and I times the parent of this vertex, and k minus I minus 1, or I could do it vice versa. I mean, this could be I, and this k minus I minus 1. No difference. And then I have another for and update dp's of parent of a and I plus 1. I add dp of a and I to it. And then I say that num of parents of I minus 1. And then if it was 0, if it became 0, it means that all its children are processed. I mean, when a child is processed, I subtract 1 from num of parents of I, because it now has 1 less unprocessed children. If it was 0 and it was not the root, parent of a was not 0, then I say q dot push parent of a. And then I say q dot pop. This way everything will be calculated. And so everything will be calculated, and then I will see out answers. I only do not push roots there. I mean, I will not push vertex 0 there, because 0 does not have any parents to update it. Basically, I could do everything in DFS, because in DFS also I'm doing the same thing. First, I'm finding the answers for if you look at this code for DFS, basically I'm doing the same thing. First, I'm calculating these values for the leaves, and then, basically what I tried to do was to start from the leaves and go upwards and update everything. I wanted to start from the leaves and go upward and build everything. In my DFS, I'm also doing the same thing. I'm going downwards and then build them and come back. I mean, basically in my DFS also I'm making everything upward as well. These values are first being calculated for the vertices that are below the others, and then I go upward. So I mean, basically that is happening in this DFS as well. Does it make sense? I know that it might be a bit complicated, but I hope that it makes sense. No, I haven't yet covered it, but in future, yeah, sure. No, sure. dp of v and I times dp of u and I minus dp of v and I times dp of u and k minus I minus 1. Well, the reason behind that is if I find a vertex at distance I from v, I know that u is also a child of v. So I can multiply it by the number of vertices at distance k minus I minus 1 from u. I mean, if you consider a vertex at this distance from u and a vertex at this distance from v, the point is that this path between them is gonna have exactly k vertices, because there are I vertices in here, one vertex in here, and k minus I minus 1 vertices in here. So it's gonna have k vertices in total. Yeah. Does it make sense? dp of u and I minus 1 may be out of bound. Let me see where are you talking about? Oh, yes. Yeah, we can say that instead of this, we can, yeah. If we say this, we should say that if I was not 0. Or fix it in a better way. But, for example, we can say if I was not 0, dp of v and I plus equal to dp of u and I minus. Yeah, we have online compilers here, so you guys are compiling this code in your mind. Is this binary lifting? No. I mean, we're just solving problems right now. This was the second problem. This was the second problem that we solved. Okay, shall we move on to the third problem? Are you guys ready to discuss the next problem or not? Thank you for random emojis. Yeah, and guys, you can always watch the whole video in here as well. I mean, any part of the video, you can watch it in here. And after the stream, the stream will be saved as well, and you can watch it after the stream as well. The best resource for trees is Codeforces. Thank you very much, Said Abdullah. Yeah, the best resource is Codeforces itself. You can just choose all the problems, you tag trees and start solving them. That's the best resource. Because the main important thing is to solve so many problems. That's the most important thing. And CF is the best source to find problems. Okay. So now let's move on to the next problem, to the third problem. Guys, the third problem that I wanted to discuss was this one. I mean, 319D, capital, choosing capital for Treeland. Let me first bring something. The point is that this was the problem that I would discuss right now if I hadn't covered it before. This problem, choosing capital for Treeland, 219D. This is a very important problem as well. This is DP rerouting idea. So again, you will see that this is a problem on trees. This is again a problem on trees that uses DP. Okay, this is a very famous idea, DP rerouting idea. And this was the topic that I would talk about right now if I hadn't covered it before. But because I have covered it, I put the link to this video here. I mean, this is the video that I had for DP rerouting idea. In here, I will send you the link to this video and you can watch it there. You can just watch it there. So the third problem here, you can watch it in here. This is DP rerouting idea. Please make sure to watch this one as well. Please make sure to watch this one because this is also a very important topic. I was thinking of maybe talking about it again, but I thought maybe it would be better if I just send you the link to the video and this way solve some other problem instead of that to solve more problems. This is a very important idea and I have made 2 videos about it. We have DP rerouting 1 and also DP rerouting 2. There are 2 is a bit more challenging problem. DP rerouting one is a 1700 problem, difficulty problem. The other one is 2000 plus, more than 2000 difficulty. So please make sure to watch that one as well, and then we can now move on to the next problem. Yeah, briefly, if you want me to briefly explain the topic is about calculating the answer for one node. I mean you want to find some DP for all the nodes of a tree. You will first calculate all the answers for one node, for example for the roots, and then from that answer for the roots you will calculate the DPs for all the vertices. So the main thing is that when you want to calculate DPs of all the vertices, you will only calculate DP of the roots, and then using the DP of root you will calculate the DP of all the other vertices as well. Yes. You do not need to know anything. You can watch the video to understand DP rerouting completely, and the next problem up here does not use DP rerouting as well. Yes, I've chosen all the problems in a way that it would be very easy for all of you guys to follow them up. I mean, as you saw in the first two problems, you do not really need any some specific knowledge about some advanced topic. If you know only what are the trees, you know some basics, you will understand the solutions. So now let's move on to the next problem. If you guys are ready for it now. The next problem is from Atcoder. It's this problem, shorten diameter. This problem is from Atcoder, Atcoder Grand Contest 1, Task C, shorten diameter. This is also a very good problem. And it is from the first Grand Contest of Atcoder. You know, Grand Contests of Atcoders have so many great problems, so many problems that are really great. And especially the first Grand Contest of Atcoder had awesome problems. I think right now maybe it's not that good, but it still is very, very good. But the first Grand Contests of Atcoder were awesome. I liked their problems the most, seriously. I mean, they were awesome. So let me talk about, for example, even in this contest, if you see problem E, BBQ hard, this problem was, for example, very interesting, or some other problems as well. So let me now talk about this problem, shorten diameter. It says that you are given a tree, and distance between U and V is the number of edges on the simple path from U to V. The diameter of a tree is the maximum among the distances between any two vertices. So the diameter is the maximum distances between two vertices, maximum among the distances between any two vertices. We will call a tree good if and only if its diameter is at most k. You are given an undirected tree with n vertices numbered 1 through n. For each I, there is an edge connecting vertices a sub I and b sub I. You want to remove 0 or more vertices from the tree so that the resulting tree is good. When a vertex is removed, all incident edges will also be removed. Find the minimum number of vertices you need to remove in order to produce a good tree. So it says that you have a tree and you call a tree good if and only if its diameter is at most k. You want to remove some of the vertices so that you will have a tree at the end and its diameter is at most k. The tree is good. You have to say that how many vertices you need to remove, at least. And n is up to 2000. Is the statement clear? So let me also say it on tablet. N is at most 2000. We have a tree of n vertices. We want its diameter. Diameter is the maximum pairwise distances, maximum distance between two vertices. We will say that a tree is good if its diameter is at most k. We want to remove minimum number of vertices such that the diameter will be at most k, such that the tree will be good. You want to remove the minimum number of vertices. And definitely, after removing those vertices, your graph must remain a tree. It must not become disconnected. So, What can we do on this problem? Well, basically, there are going to be two cases. Basically, first, let's assume that k is even. K can be odd or can be even. Well, the point is that if k is even, if diameter is k, well, there's something that we define in a tree. It's a good time to learn this as well. I mean, we understood that what diameter means. So you learn the definition of diameter if you didn't know already. Now there's another important thing in a tree, that is center. A center of a tree is the vertex in the middle of the diameter. So for example, if k is even, this is going to be exactly the vertex in the middle. And if k is odd, there are going to be two vertices in the middle. So both of these two could be considered as the center. The main important thing about the center is that its distance to the farthest node is minimized. I mean, the maximum distance from center to every node is minimized. The point is that if you pick the center, you know that the distance from center to the farthest node is at most k half. You can easily prove that. I mean, if you consider the diameter of a graph, it is k, diameter is k. Let's pick the vertex in the middle. We know that there are k half vertices, k half edges in here, and k half edges in here. K was even. You can easily show that no vertex has distance more than k from this center. More than k half from this center. Because if any vertex have distance more than k half, it would have intersection with at most one of these two left and right part of this path, and you can consider it, because this is greater than k half, you can consider it with the other half of the diameter, and it means that you will have two vertices with distance greater than k, which is a contradiction. That's not possible. So I showed that if a vertex has distance more than k half with the center, the diameter must be greater than k, which is a contradiction, because I showed that the diameter is exactly k. So the main important thing is that about the center is that the distance to the farthest node is at most k half. So this gives us the idea of what we should do. If k is even, I know that n is at most 2000. So I will iterate on all the vertices. I assume that this is going to be my center. The point is that I must remove every vertex. I mean, I do a DFS from this vertex, and I will find the heights of all the vertices. Any vertex that its height is greater than k half must be removed. So I will fix each of the vertices as the center, and I will find out the heights of all the vertices. All the vertices that their heights are greater than k half will be removed. I count that how many are there, and I consider the minimum of them for all the possible c's. And the minimum of them is going to be the answer. And this is how the even case of k will be solved. Does it make sense? Is it clear? Again, if it is clear, please use this emoji or put a plus in the chat. Or if you have a question, you can ask as well. So basically, the idea was that we pick a vertex and we keep all the vertices within distance k half from it. Vertices with distance greater than k half will be removed. Yes, exactly. We first fix the root that all the vertices must have distance at most k half from it, and then we will count that how many vertices must be removed. Yes, it is a brute force idea, exactly. It is a brute force idea. We will brute force on the roots. Because n is at most 2000, we can each time choose one of the vertices as the root and run a DFS. So it's going to be n squared. Because we have a DFS on 3, the order of DFS is n, and we have n DFSs, so it's going to be n squared. Do you have any other question? This is how case K, even case of K will be solved. Nice, thank you. Any other questions? Nice. Thank you guys. So now exactly we have to consider the odd case of K. So now consider that K is odd. So the point is that, as I said, when K is odd, we have two vertices in the middle. We don't have only one vertex, we have two vertices. So it's like we have an edge in the middle. So we can fix that. What is this edge? Again, we can say that the distance of each vertex from this edge must be at most K minus 1/2. Now because K is odd, I use K minus 1/2. I can say that the distance for each vertex to this edge, by the distance to this edge, I mean the distance to one of its endpoints. It must be at most K minus 1/2. Because again, I can show that if it's not the case, if there is a vertex such that its distance from this edge is more than K1/2, again, more than K minus 1/2, again, it will ruin at most one of these two parts. It will have intersections with one of these two parts. I can consider it with the other half, and this makes a diameter greater than K. So again, I can say that there must be an edge such that its distance to all the vertices is at most K minus 1/2. So this time I can fix all the edges. There are n minus 1 edges. So again, there are O of n DFSs. I set the height of both of its endpoints to 0. And then I will again find out how many vertices have height greater than K minus 1/2. So basically I can just, for example, if this is U and V, I can first once run DFS of U and give V as its parent, and once use DFS of V and give U as its parents. This way I make sure that V will not call U and U will not call V. And initially you can set their heights equal to 0 as well. So you can set heights of U and V as 0, and then call DFS of U and V and DFS of V and U. This way this part will be found out by U, this part will be found out by V, and then we can see that in each of these parts how many vertices have height greater than K minus 1/2, and we can just count the number of them and find the minimum possible way for that. Is it clear? We start removing we start from the leaves, right? The point is that in our solution, yes, I mean we start removing from the leaves, but the point is that now we are just counting that how many vertices we will remove. We are just counting that how many vertices we will remove. So we are not giving an answer of how they are going to be removed. I just count that how many vertices have distance greater than this fixed distance, and I say that all of them must be removed. I don't choose that in which order they're going to be removed. But yes, if I wanted to choose that in which order they're going to be removed, it was better to start removing from the leaves so that the tree will not be disconnected. Don't we have two centers in even case? I think you have said opposite. Please correct me if I am wrong. Well, by K I mean the length of the pass. Okay, by K I mean the length of the pass. So the number of edges of the pass. So when K is even, there are even edges. When K is odd, there are edges. So for example, when K is even, for example, we have 4 edges. This is not the number of vertices. This is the number of edges. So when we have 4 edges, there is exactly 1 vertex, such that there are 2 edges in its left and 2 edges to its right. So this is the number of edges, not the number of vertices. If it was the number of vertices, it was opposite. Right. Awesome. So is this case clear as well? Did you understand it well? I had a doubt that while removing with the center shift, and one more doubt that doesn't. From which side? Yeah, that's right. The center will shift, but the point is that we do not care about the center of the tree, center of the original tree. We are talking about center of the final tree. I mean the tree that we make. So this is not the vertex, this is not the center of the original tree that we have. Yes, that center will change. I mean, as we remove the vertices, the center will change. I'm deciding that which vertex I want to be the center at the end. Which vertex I want to be the center at the end of the process. So I mean that I just care about after removing all the vertices and made the tree good, I know that my diameter is going to be k. Either it is initially less than k and it is initially good, I mean the tree without removing any vertex is good, or it has diameter greater than k. If it has diameter greater than k, we have to make its diameter k. And the point is that when we make the diameter k, I mean I'm considering that final tree. I'm saying that, okay, that graph must have a center. And okay, if this is gonna be the center, I have to remove every vertex that its distance is greater than k half from it. So this center is the center of the final tree. It's not the center of the tree at the beginning. Yes, that center would change and would not remain the same. Is it clear? If we find two maximum lengths where the skewed passes downwards from each node, will we be able to solve this? I think it would be a bit problematic. I mean, it would be hard to do that. I mean, the best way is to do it like this. I think if we just find two passes, there are gonna be some problems on how you want to remove the vertices and keep track of all the data that you need to find out how far the rest of the vertices can be. I think that would be problematic, and you need to think about it this way, because this way everything would be so easier. You just fix a vertex and run DFS. Everything that had distance greater than k half, you will count them, how many of them you have. I will show you my code as well. Just a suggestion, please make video of Atcoder beginner contest. It will be helpful for beginner like me instead of lead code contest. I see. So you guys want to cover beginner contests of Atcoder? All of you believe the same? We can try to cover that, but in the past weeks there was a CF contest as well at that time. I think, for example, last week it was like that, but if you guys want, we can try to cover Atcoders as well. Yes, we are brute forcing on all the nodes that can be the center at the end. Yes. Let me also show you the code that would also help understand it better. Let me bring it. This is my code for this problem. Wait a minute. You know, I remember that back then I accepted all these problems of the first grand contest, 2017. So it's crazy that's how many years has passed from then. Anyway, so let's talk about this code. What I'm doing is that I get all the vertices, I make the tree, and then I say that if k was odd or if k was even. For example, if consider this case else that k is even. In this case, I have a 4 on all the vertices, and I set them as the root, as the center of the tree. And then when I do this in here, I run a DFS, and I divided k by 2. Now I have to find out all the vertices that their height is greater than k, because they must be removed. Because k is now k half, and now I have fixed the center, I have to find out all the vertices that they are at height greater than k. So I do this DFS, and I just say that if height of this vertex was greater than k, add 1 to the value that needs to be returned. and then I say that each time I will go to a child, I will add 1 to the height. I will tell you that what this CC means. This is for the odd case. But anyway, in the even case, CC is going to be -1, so it does not have any effect. I will add 1 to H, and I will go to this vertex, and at the end I will return this ret. This is going to be the number of vertices with height greater than k. In the case where k is odd, I just also, other than picking a vertex as the root, I will also choose one of its adjacent vertices, and I say that, okay, the height of that one is going to be 0 as well. That's where this CC matters. That's where, when I go to that CC, that J, I will not add 1 to H. And its height is going to be 0 as well. So you can both do it this way, or like what I said, run DFS of U and V and run DFS of V and U as well. So just run 2 DFSs and count the number of vertices at height greater than k. So anyway, the main idea is to fix a vertex and find out all the vertices that are at distance greater than k from it. And this way everything can be calculated. Can we solve it under O of n log n? I don't think so. It would be, yeah, it doesn't. Look, that's a very interesting question to ask, but I don't guess so. So do you have any other questions about it? If you are okay with that, please use this emoji or put a plus. Otherwise, if you have any questions, you can ask now. Is it clear? Shall we move on to the next problem? Okay, sure. Nice. So then let's move on to the next problem. The next problem is problem K3, again from Codeforces. This is the next problem. Let me send it to the chats. This problem says that quite recently a creative student, Lasha, had a lecture on trees. After the lecture, Lasha was inspired and came up with the tree of his own, which he called a K tree. This tree is like this. Each vertex has exactly K children. Each edge has some weights, and if we look at the edges that goes from some vertex with children, exactly K edges, then their weights will equal to 1, 2 to K. And this is an infinite rooted tree. It's infinite. So all the vertices have exactly K children, and it will go infinitely. All the vertices have children. So again, these ones have children as well, and so on. Infinitely they have children. Each vertex has exactly K children. Each edge has some weights, and the weights are exactly 1, 2, 3, 4, 2K. Okay, and again, that vertex again has edges 1, 2, 2K. And so on. And now the question is that how many passes of total weight n do we have such that the sum of all, n is the sum of the weights of all the passes, such that the weight of at least one edge is at least d. So how many passes do we have from the root such that its weight is n and it has at least one edge of weight at least d. So one of the edges must have weight at least d. All of them should not be less than d, in other words. So you need to find the answer to this question. Okay, so let me explain it in here as well. So you have a K tree. It means that you have a root and it has K children. Each of the vertices have exactly K children. And the weights are 1, 2 to K for every one of them. And it will go infinitely. It will go infinitely. You have to find out the number of passes from the roots to some vertex such that this weight, the weight of this pass is n, and you have at least one edge of weights at least d. Okay, you need to find that out. So first of all, let's simplify the problem a little bit. Let's say that, let's forget about this being at least D. Let's say that you just want to count the number of passes of length n. This problem is really helpful because it says two important things. So first of all, you are getting familiar with what is a tree, infinite tree. I mean, you get familiar that we can have an infinite tree, and a tree can continue forever. I mean, usually trees are finite. For example, they have n vertices and n minus 1 edges. But in some problem like this, you can also define something like this, that you have an infinite tree and each vertices have children and they will go infinitely. And also this problem is important because this is a tree problem. Oh, you cannot see the screen, right? I think you cannot see the screen. Okay, so let me continue explaining until it gets fixed. So basically, you want to find out something, and this problem also has this advantage that shows that this is a problem that looks like a tree problem, but it's not really a tree problem. This is a problem such that it has the looks of a tree problem, but tree is not very important in it. It's not really a tree problem. It's not. It does not use tree algorithms or something like that. So it just looks like a tree, but the tree is not very important in it. Let me connect it again, and I hope that it gets fixed now. I hope. Yeah, we have these technical issues sometimes. Let's hope that it will be fixed. So for now, let me continue in here on laptop. So basically, as I said, let's for now assume that we just want it to have length exactly equal to n. We want its length to be n. We do not care about that one of the edges must be at least d. So we only want the weight to be equal to n. Well, the point is that when we start from the root, we can say that the first edge has weight 1 or 2 or 3 or to k. So we can have a for I from 1 to k and fix that what is the weight of the first edge. And then we can say that, okay, then after that, from there, we have this weight I. Again, it's like our root is here, and we are now looking for a path of weight n minus I. So I can say that it's like dp of n will be added by dp of n minus I. Because we can say that what is going to be the length of the first edge is going to be either 1 or 2 or 3 or to k. And then we go this edge, and again, we're going to have the same tree. Because the tree is infinite. Again, we have a tree such that this vertex has k edges, all the children have k edges, all the children of children have k edges, and so on. So again, we have the same situation, but now we are looking for n minus I. So I can say that for each n, dp of n will be added by dp of n minus I for each I from 1 to k. I from 1 to minimum of n and k. I cannot be greater than n. And I can this way calculate all the dp's. So every n, for every possible value of n, its dp of n is going to be the sum of dp of the last k dp's. And because n and k are both up to 100, you can easily calculate that, right? So everything will be easily calculated this way. Does it make sense? It seems like it doesn't scroll completely till the end, because I see something here. Okay, is it clear so far? If it is clear so far, please use this emoji or put a plus in the chats. And let me also check if tablet is fixed now. It's not. It's weird. But let's continue for now. Let me also see if I can do something. I mean, the whole thing that I'm doing, I'm trying to connect it again to see what happens. I'm not doing any advanced things, but I hope that it works. Okay, nice. Nice. So this is the whole thing that we do in order to find out the number of passes of length equal to n. Now we want to make sure that one of the edges, at least one of the edges, have length at least d. Well, in order to do that, I can try to find out all the bad passes among these passes. Assume that a pass is bad. What is the characteristic of a bad pass? Can you say it? Can you say that what is the characteristics of a bad pass? Yes, n denotes the sum of all the edges from the roots. Yes, all of the edges must have weights less than d. All of the edges. So do you agree that it's like I'm having the same problem, but instead of k, I have d minus 1. It's like this time, still not working, awesome. It's like this time, instead of having children 1, 2 to k, my children are from 1 to d minus 1. Each time I choose a vertex with weight from 1 to d minus 1. This time. So basically, what is happening is that I do the same thing. I again calculate the answer. It's like I have a function. I have a function f that I give n and k to it, and it gives me the answer. I have to give f of n and k, and from it I should subtract f of n and d minus 1. So basically, this way the answer can be calculated. It's going to be f of n and k minus f of n and d minus 1. If I find that for all the edges from 1 to d minus 1, I mean if I only use edges from 1 to d minus 1, in how many ways I can make the sum of the weights to be equal to n, I can just subtract them, because this is all the weights that all of the edges have weight at most d minus 1. And if I subtract them, all the remaining cases have at least one edge as with weight at least d. And this way simply it will be calculated. Everything will be calculated this way simply. I'm just subtracting the cases where at least where all the edges have weight at most d minus 1. Does it make sense? So you see that sometimes when instead of calculating good cases, we calculate the bad cases and subtract them, how everything would be simpler. How everything can be easier for us to calculate. Instead of trying to find out in how many ways at least one edge has weight at least d, I say that, okay, let's assume all of them have weights at most d minus 1. How that would be solved? And that was very easy. I mean, it was just, I assumed that my k is d minus 1 this time. And each dp will be the sum of the last d minus 1 dp's. Is it clear? Guys, do I write better with touchpad or with pencil? I mean, tablet pencil. You know, I have experience of writing with touchpads for many years now. I mean, after COVID, I had a lot of online classes, and in all of them I was using my laptop and I was writing with touchpad a lot. So right now I write with touchpad as easy as writing with pen. And I'm not sure even which one I write better. Anyway, are you guys ready to talk about the next problem? How many problems have we solved? Let's see which one of you followed so far very well and know that how many problems you've solved so far. Yes, I can explain the code. Yeah, I will show you the code as well right now. Yeah, exactly. We have done 4 problems, and I sent you the link to one of the problems as well. I will put all of the problems in Telegram channel as well. I will send you the link of the Telegram channel as well for further discussions. You can join that Telegram channel. I know that most of you are already members there, but if some of you is not, one of you is not a member, feel free to join. You're more than welcome to join there. And let me also show you my code for this one, as you guys said. For my code, I can say that this is gonna be the everything that I do. This code is new. I mean, because I wrote it in 2024. It's interesting. I did it for training in 2024, but the first time I did it was in 2015. Anyway, let me show it. Let me show you the code that I did 10 years ago in 2015. Basically, what I do is that I see in n and k and d, and as I said, I see out f of n and k minus f of n and d minus 1. Once I use this k, and once I use d minus 1, where each edge has d minus 1 children, and only we use those d minus 1 children. Only we use the vertices with weight at most d minus 1. And in here I use recursive function, and dp of x and y means that how many ways do we have, and I just recursively I say that dp of x and y plus equal to f of x minus I and y. And in f, if dp is already calculated, I just return dp, otherwise I calculate it. This is one way, but I think if I show you the way that I implemented recently in 2024, it's going to be better. Only the tabs are ruined, sorry about that. The tabs in here are ruined, they are double sized. But anyway, so I say that I define 2 dp's. dp1 is for the case where all the edges are at most k. dp2 is where all the edges are at most d. So I say that ps of I just says that in how many ways, I mean dp just says that how many ways do we have, ps says that what is the prefix sums till there. ps1 of I is equal to ps1 of I minus 1 plus dp1 of I minus 1. And I know that, as I said, dp of n is going to be equal to the sum of dp of some consecutive dp's. dp of n is going to be the sum of some consecutive dp's, so I can calculate it using a prefix sums as well. So I can say that L is equal to maximum of 0 and I minus k, R is equal to I, and dp1 of I is going to be ps1 of R, prefix sums till R minus prefix sum till N. And I do the same thing for dp2. The only difference is that instead of k, I replace this k by d minus 1. In both of the ways, I can just calculate the dp's. I mean, if I use the way that I use in this code or the previous code, I'm just calculating the dp's. And then when I can be able to calculate the dp's, I do it twice, once with k, once with d minus 1. And I will subtract this second dp from this first one and calculate the answer. Does it make sense for everyone? I have started with graph series. I have already some graph videos in topic streams. Let me also send it to you guys. You can view all of the topic streams that we had so far in this playlist. We have covered a lot of topics, from dynamic programming, trees, number theory, graphs. What should be ideal sequence of competitive programming? We will talk about these things in more detail. Right now we'll talk about trees, but in general, I had some guideline videos. I've sent it so many times as well before. Right now I have 2 videos for guideline videos, especially about if you are a newbie and you have already started, you are a beginner right now. It's here. I have talked about the things that you need to do and the things that you should not do if you are a newbie right now. I can't pass 1400 in CF. What to do? Just don't give up and solve so many more problems. You have to solve so many problems in order to be able to, in order to be able to solve them in a contest. So you need to solve a lot of problems from Codeforces. Yeah, thank you very much, Kush. You can view those videos as well there, and then watch this video afterwards if you want. So I think we have only a limited time left. Are you guys ready to talk about the fifth problem as well? Can't we just find the ants without doing total minus not ants? Yeah, the point is that calculating total minus not ants is way simpler than calculating ants. Calculating ants would be problematic because you want one edge to have weight greater than or equal to d, and it would be problematic that how can we do that? For example, you want to fix one of the edges, and then you say that before that you only use less than d, after that you use anything you want. I mean, that would be problematic. But if you consider not ants, not of ants, you are sure that all of them are at most d minus 1. And this is way easier to calculate when all of them are at most d minus 1. And easily you can calculate that. Why is it that some people get high rating very fast, but people like me struggle at specialists? I mean, it's the way you're training as well. I mean, the main reason that we are doing this YouTube channel, we're doing these topic streams, is to help you guys do that in an easier way. I mean, provide some materials for you to be able to study to do that better. And let me say this to you guys as well. This is also very important. I talked about an idea yesterday in Telegram that we can do in the future topic streams. Do you guys know what I'm talking about? Boolean in recursivity, we can take only those solutions for which Boolean are true. If you mean Boolean for calculating the answer, for avoiding calculating the answer again, that's the main thing that we do in order for memoization. If you mean that Boolean for memoization, you have to do that if you do recursive function. But if you mean it for something else, I'm not sure. I haven't understood completely. Yes, the idea was that, you know, we solve so many problems in these topic streams, and the point is that we can just have a contest for you guys, a contest that you guys participate in. I put all these problems in a contest in Codeforces mashup, in a Codeforces group, and you can participate in that contest. First try to solve the problems yourself, and then I come to the topic stream and try to solve the problems for you guys. So what do you guys think about this idea? This is just an idea. I want to see that what do you guys think. If you guys think that is going to be helpful, we can do that. I have discussed it with you in a Telegram channel. If you want, you can join the Telegram channel and we will discuss it further with you guys. So do you guys like that? Nice. So we can do that. I think this is something that we can do from the next week. We can do some. We can make some Codeforces group that you guys can join and participate in those contests, and then we will solve it in topic streams. I haven't yet done any lead code streams, no, but I have the plan of maybe doing it. If that is going to be helpful, lead codes and Atcoder and things like that, that might be helpful for you. Please do a stream on interactives. I have no idea how to solve those problems. Yeah, sure. We'll definitely move on to those ones as well. Permutation graph. Sure, we'll discuss them. All of them are in our list. Each week we're gonna have a topic stream, so hopefully we can go on all of these topics and cover all of these topics. Hopefully, because yeah, I believe that because each week we're gonna have a topic stream, that is gonna be a great opportunity for us to move on all of these topics. Nice. How many of you guys participate in lead codes and how many of you guys participate in Atcoder? I mean, if you you can either write this, or if you participate in lead code, you can use this. If you participate in Atcoder, you can use this. This might be a bit hard to follow these emojis. But if you want, I think that would help me to find out how many of you can participate in LeetCode, how many participate in Atcoder. You can use this for LeetCode and this for Atcoder. I think I forgot it already as well. Atcoder, both LeetCode. Which laptop computer do you use? I use this M2 MacBook Pro. Okay. Maybe we will start discussing LeetCode and Atcoder as well from the next. I'm not only solving Codeforces contest, but also LeetCode and Atcoder as well. Right, I see. Okay, so maybe now let's talk about the last problem of today's problems as well. The last problem that we want to discuss today is Book of Evil 337D, Book of Evil. Let me send it here. This problem says that, we have a tree and there is a Book of Evil somewhere in your tree. There is a Book of Evil and it is somewhere in one of the vertices of your tree. And you know that this Book of Evil has a damage range of D. So if it is in any vertex, its damage range is exactly D. So it can damage all the vertices that are within distance at most D from it. Okay, so it can damage all the vertices that are within the range at most D from it. We know that some of the vertices are damaged. So we are given M vertices, and we know that M vertices are damaged. P1 to PM are damaged. Maybe the rest of the vertices are damaged as well, but these are the vertices that we know for sure that they are damaged. Okay. And you have to say that in which vertices the Book of Evil can be, based on these vertices that we know that they are damaged. So basically, we know that a Book of Evil is in one of the vertices, and it will damage any vertex that within range at most D. We know that some of the vertices are damaged. We don't know anything about the rest of the vertices. Maybe they are damaged, maybe they're not. We want to see that in which vertices the Book of Evil might be. Okay. Or in other words, we basically want to find out. It's like we have M vertices in a tree. Let me draw the tree. In other words, we have M vertices in a tree. And we want to find out all the vertices such that their distance to all of them is at most D. So you want to count that how many vertices exist so that the distance of that vertex to all of these vertices is at most D. Those vertices might have Book of Evil because their distance to all of these vertices is at most D. If some vertex has distance more than D to one of these vertices, Book of Evil cannot be there because it has no chance to harm that vertex. Okay, so we want to count. In other words, we have M vertices in a tree. We want to see that how many vertices exist such that their distance to all of these vertices is at most D. And N is at most 10 to the 5th in this problem. Is the statement clear? Isn't it like the second problem? Not that much. The second problem, you mean 161D? That was counting the number of pairs with distance k. It's not exactly like that. Put all damage vertices in Q and run BFS. Well, there's one problem in doing that. If we put all damage vertices in a queue and run BFS on that, for each vertex we will find its distance to its closest damage vertex. But in here, we don't want the distance to the closest damage vertex. We want the distance to the farthest damage vertex. Because a vertex might have the Book of Evil if and only if its distance to the farthest to the farthest damaged vertex is at most d, not to the closest one. If you run a BFS, you will find the distances to the closest damaged vertex, not the distance to the farthest damaged vertex, right? So that's the main important thing. You want to find out the distance of a vertex to the farthest one of these damaged vertices. Okay. And in order to do that, we will have an idea that is very, very well known and extremely helpful. This is called DFS up, DFS down. And it is extremely helpful. I hope that you will understand it completely. So focus on it. This is going to be super important. So I have m vertices. From each vertex, I want to find the farthest one of these m vertices for each vertex in tree. Well, the main idea is that first of all, I will try to find the farthest node from each node in its subtree. So first of all, I will try to find out among those m nodes, among the ones that are in the subtree of this vertex v, what is the farthest node? I only try to calculate that, try to find out all the vertices that are farthest in the subtree of vertex v. And that is relatively easy to calculate. I mean, we can just run DFS on every damage. That would work, but it's slow because n is up to 10 to the 5th. So that's correct, but it's slow. It will have a TLB. So basically what we will do is that first of all, we try to find out the answer in the subtree of the vertex in our DFS1. This code is again from 2015. A lot of my codes are from 2015 today. So we first of all, we want this U, this D1, this D2. I mean, we want to find out, first of all, we only care about downwards. In DFS1, we will find out that what is the farthest node in the subtree of this vertex. If we go down from this vertex, what is the farthest node? So the marked vertices are the ones that are damaged. Initially, I set all the distances to minus infinity. For all the vertices. If there is no vertex in the subtree, it would be minus infinity. The answer for it would be a negative number. Let's assume that I want to find out the farthest vertex in the subtree of this vertex. If there are no damaged vertices in the subtree, I will just put a negative number there. So I initially set minus inf here, and then I say that if this vertex was marked, this was a damaged vertex, and this vertex downward was less than 0, I set it equal to 0. Well, the point is that, let's forget about this line for now. I will talk to you why this is important. And then each time I will go to a child and I will update this vertex from that child. So basically what I'm doing is this. I will have a child like u. When I have a child like u for v, I will just say that distance of down of v will be maximized by distance down of u plus 1. So it's like this d of v will be maximized by this d of u plus 1. Because if u has a distance to a damaged vertex, v has that vertex in its subtree as well, and its distance it's going to be equal to the distance of u plus 1. So basically this way we can calculate the farthest node in the subtree of vertex v. Right? This way easily we can find the farthest node in the subtree of vertex v. Does it make sense so far? Does it make sense that how we can calculate the farthest node in the subtree of each vertex? Initially we set all of them to minus infinity, and then for each vertex, if that vertex was damaged itself, we set it equal to 0, and then for each child we set it equal to that plus 1, maximize with that 1 plus 1. Awesome. Now let's say that we calculate the two farthest ones. We will see that why two farthest ones are important. The main idea is that now I want to find out the farthest damage node out of the subtree of vertex v. So far I found out that what is the farthest node in the subtree of vertex v. Now I want to find out what is the farthest one outside of subtree. It can be anywhere outside of subtree of v. In order to calculate that, I need two vertices in the subtree of two farthest vertices in the subtree of vertex V, and we will see why in a bit. So basically, that's why you saw in my code in here that I'm calculating two distances. The point is that you will see why this is important and why we need it. The point is that from each vertex V, not only I want to find out the farthest damage node, but also I want to find the second farthest one that is in another subtree, in the subtree of another child of V. So for example, if this farthest node is in the subtree of U, I want to find the second one that is in another subtree that is not in the subtree of U as well. For example, that is in the subtree of another child of V, like U prime. So I want to find out, if for example in the subtree of vertex U, I have the farthest one, I want to see that what is the second farthest one as well that is in another subtree. And we will see that why it is helpful very soon. Why it is helpful to find out the distance to the outside when we want to calculate the distance to the outside of the subtree. So basically I calculate two distances. Each time, first I update distance 2 when I add anything. I just update distance 2. And if distance 2 afterwards, I said that if distance 2 was greater than distance 1, swap distance 1 and distance 2. So from now on, I will always update distance 2. I had two vertices. First, distance 1 is the maximum one, d1 is the maximum one, d2 is the second maximum. Each time I will update second maximum. If second maximum was getting greater than first maximum, I will swap these two. So I say that if this d1 of var was less than this d2 of var, swap these two. Again, when I add a child, I first calculate everything for it. If it can update this 2 of var, I will update it. So I say this d2 of var is max equal to this d1 of u plus 1. And then again, if this d2 was getting greater than this d1, swap this 2. So this way, easily I'm updating everything. Okay, I'm calculating the two distances. Yeah, sure. No problem. Good luck in CodeChef contest. So basically, this way I'm calculating the two greatest distances that I have in the subtree of vertex V. And what I say is this. I say that when you want to find out the farthest node when you go upward from vertex V, you want to find the farthest node. You know that what happens in the subtree. Now you want to see what happens outside of the subtree. So first you need to go to your parent. Your path first goes to your parents, goes to P of V. So I can say that the farthest node, if I go upward from V, first of all, I need to go to parent of V. And after that, either from parent of V, again I will go upward. So I will go out of the subtree of the parent as well. In this case, I'm going to have up of parent of V plus 1. I assuming that parent of V has been calculated before V. So before coming to V, I have calculated the answer for parent of V. So I know up of P of V right now. So in downwards, when I was going downwards, first children will be calculated and then the parent will be calculated based on the child. In here is vice versa. I assume that I know up of P of V, and if I go from V to P of V, again if either I will go upwards, so it's going to be up of P of V plus 1, or this time I will go downward. When this time I will go downward, I need to make sure that I will not go back to the same child. I should not go back to the subtree of V again. Okay, I need to make sure that I will not go back to the subtree of V again. This is where calculating two farthest nodes in the subtree will be helpful. Here we can say that if I know two farthest nodes in the subtree of vertex V. The point is that basically I need to go to the farthest node in the subtree of vertex P of V. So basically it needs to be d1 of P of V plus P sub V plus 1. If it is, hopefully in another subtree, but if d1 of p sub v is inside the subtree of v, I should use d2. Because d1 goes to the subtree of v again, so instead of that, I should use d2 this time. Because d1 goes to the same subtree of v, I should go to the second farthest node in the subtree of p of v. So basically, this is why we needed two farthest nodes in the subtree of p of v. Because maybe the farthest node is in the subtree of v itself, and we cannot go from v to p sub v, and then from p sub v again go back to v. That is not going to be a simple path. We should go to another subtree. Therefore, we need to consider d2 of p sub v in that case. Or if I show you on code, let me see what you ask. I don't completely understand what does it mean, but you're welcome for this. Thank you. We will talk about this later as well. So let me tell you about this part. I'm saying that if parent of vertex, first of all, I say that if this vertex was marked, distance u of it is equal to 0. Because right now, so far, I found one vertex. Initially, it was minus inf. So if this vertex is damaged itself, 0 is an option. So initially, I can set it to 0. It's not a negative number anymore. Then I say that if parent was not minus 1, I can say that this u of var first equal to max of this u of var and this u of par plus 1. And then I want to calculate this d of par, this d's of var. I say if this d1 of par was not equal to this d1 of var plus 1, it means that if it was not updated from this vertex, if distance 1 of par is not from this vertex, if it was not equal to this d1 of var plus 1, this u of var will be max equal to this d1 of par plus 1. Otherwise, it would be max equal to this d2 of par plus 1, because the first distance downward from parent uses the subtree of vertex var. So I need to use the second one of it, so that I'll be sure that it's going to be in another subtree. Okay. And then at the end, I just have a 4 on all the adjacent vertices and run another DFS on them. And this way, I will calculate distance up of each vertex as well. At the end, maximum of distance up and distance down must be less than or equal to d. If it was like that, I will add 1 to the answer. And at the end, see out answer. This is called DFS up, DFS down. And this is a very interesting and very important topic. I will solve more problems using it. Also in DP rerouting idea, you will see the idea of DFS down and DFS down up again. You will again see DFS up, DFS down idea in there. In DP rerouting, this idea can be helpful as well. So if you watch that video that I sent you, that is gonna also be helpful to work more with DFS down, DFS up as well. But this is how we can find the farthest node from a node this way. We first easily find the farthest node in the subtree, and then we try to find the farthest one if we go upward. When we go upward, distance of u of var first needs to be calculated, updated by distance u of par, and then we will see that if distance d1 of par was using this d1 of var, then we should use this 2. If it was not using, if it was not equal to this, we should use this d1. And this way everything can be updated. Is it clear? Are you a fan of Trump or Kamala? I rather not talk about politics that much. I don't have that much preferences, to be honest. But what do you guys think? Are you guys a fan of Trump or Kamala? And other than discussing this important topic, if you understood the solution, please use this emoji or put a plus. And if you have any questions, let me know. You're a fan of Trump. Why? And what about the rest of you? Let's see if CP community prefers Trump or Kamala Harris. And in the meantime, if you have any question about the solution of this problem, you can let me know. That's completely okay. It takes some time for you guys to get more okay with it. As I told you, as I showed you, fan of neither. And where are you guys from? And why you are a fan of neither? Trump? Do you have any Kamala fan? So yeah, I mean, I wanted to also talk about this. If you take a look at my own plots, you will see that initially I was in newbie as well. I solved no problems, but I continued training, and then you see that I started to go up. My rating started to go up. But if you take a look at this contest, I think my performance was very poor. I think I didn't solve any problem in this contest, and this happens. But the point is that if you persist and move on, you will get better, and you will increase your rating. You see that in here I solved one problem A. Okay. So basically, release CP sheets for solving problems. Yeah, I think I can either release CP sheet or use that CP group that we're gonna have in Codeforces. I can also put the problems there. Does that work better or not? I can also use this CP group, and we can just solve the put the problems there, if that's gonna be all. Which code editor do you use? Right now VS Code, but right now I don't code for CP usually. If I use code for CP, I use Atom. It's okay, just start participating in contests again. I mean, it's not very challenging. Start participating in contests again. After that, try to upsolve problems. Try to go to Codeforces, sort problems by their difficulties again, and start to solving them. You can again watch that video that I mentioned about being a newbie. When you are a newbie, what to do, what not to do. And basically, it's not gonna be challenging. I mean, once you participate in 2 or 3 contests, you're back on track, and you can start training again. And everything is gonna be helpful. Was today's stream helpful, guys? I mean, did you learn things or not? Give me some feedbacks, and then we can finish the stream afterwards. So please give me some feedbacks. And furthermore, we didn't have any Kamala fan so far as well. So if you are a Kamala fan, you can also mention that in the chat. We had 2 Trump fans. Either 2 months is so few for achieving something. I think it's you have to spend more time anyway. I mean, you should not think, you should not have short-term plans that much. This is something that takes time. You need to have a lot of training, etc., in order to get somewhere. It takes a lot of time. So don't think that you can reach somewhere very quickly. For myself, it took me a lot of time to grow, and that's the path. Try to enjoy the path, and it's you're not gonna achieve everything very soon. You know, this question basically depends on your current rating, what is your current situation, etc. as well. But do not try to force yourself to achieve something in 2 months. Maybe it takes more. Usually, for myself, it took more than 2 months to reach 1500. Nice, thank you guys. Thank you. I hope that you enjoyed it and you have learned from it. If you liked this video, I would appreciate it if you share it with others as well, so that in the future topic streams there would be even more people. I think I would enjoy the topic streams definitely more if I see it's gonna be more effective and more of you guys are there. And in each topic stream I get familiar with more of you guys. I get to know more of you, and this is gonna be really awesome. You can finish LeetCode stream in 1 hour. Yeah, definitely. I will put it in my mind to do some LeetCode solution discussions as well. Next time, combinatorics problems. Yeah, I will put a vote. I will put a poll in Telegram channel, and I will ask you guys that's what you want to do to be discussed. Right now, no. I mean, I haven't participated in contests recently. Maybe in future, maybe in a bit long-term future. But right now, because basically the timing of the contests are not very good for me. I mean, after I came here, almost in all of the contests I wasn't available at the time of the contest, so it was a bit problematic for me. But maybe in future. Thank you guys for joining today. Yeah, I see what you're talking. Maybe we can cover that bit manipulation in future as well, in the future topic streams. Thank you for joining again. Hope to see you again in the next topic streams, and see you next time. I think 2 days from now there's a Codeforces contest as well, so I think I will see you there as well. So see you guys. Thank you. Bye bye.